Homework 15, Sampling Distributions in the Central Limit Theorem, Video 2. Is the sampling distribution of x bar normal? Because if it is, then we can use the z-table and do probabilities. Now, what do I mean by that? Well, I'm actually going to set up two histograms. I'm going to set up one for the original population, which is why I just put an x by the horizontal axis to represent the individual values. Well, making a histogram for this is easy. There's only 4 values, 1, 2, 3, and 4. All of them have frequency 1, except the number 1, which has a frequency of 2. So if I made a bar graph of that, I can ask you, is this somewhat normally distributed? Does this have a bell curve shape? I would say no. If anything, I would say it's skewed to the right, but it's a really small population, so maybe even that isn't very accurate. But I think we can all agree this doesn't look like a bell curve. But let's look at the sampling distribution and its histogram. So for this histogram, I'm going to put x bar to indicate that that's what we were measuring. Now I've already set it up with all the different x bar values from the previous example. And this time I'm going to use the relative frequencies, or the probabilities, which won't really change the shape of it, it just changes the scale. So, for 1.3 repeating, the probability was 0.1. So I can raise a bar above 1.3 repeating up to 1. The same thing for 1.6 repeating. For 2, that goes all the way up to 0.3. The probability that the sample mean is 2 is 30%. And for the next 2, they go up to 0.2. And then for the third one, it goes up to 0.1. Would you say that's approximately normal? Well, you could argue that it is or that it isn't, but I think one thing we can agree on is that this is a little bit more bell curvy than this. Namely because the peak is somewhere in the middle, it's a little bit symmetrical. And again, this is a very, 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 very small population and hence a small sample size. But let's say that we had a population that had not 5 numbers but 500, and instead of picking 3 samples of size 3, we picked all the samples of size 10. Now, we should never actually do that. Pick all the samples of size 10 out of a population of size 500. Because if we did, give me 1 second, I may break this calculator. I didn't, but what I'm about to say is going to surprise you. Let's pretend that instead of a population of 5 numbers, we had a population of 500 numbers. And instead of picking every sample that contains 3 values, we picked every sample that contains 10 values. Let me make sure I did this correct. I did. So if our population had 500 numbers and we picked every sample of size 10, how many samples do you think we'd have? 500? 5,000? A million? I'm going to write down how many samples we would have. 2, 4, 5, 8, 1, 0, 8, 8, 8. Wait a minute, I'm not done. With 11 zeros. We would have that many samples if our population had 500 numbers and we picked every sample of size 10. You realize the logistical problem with this. Number 1 is, how do you even read this number? Well, that's million, billion, trillion, quadrillion, 256 quintillion, 810 quadrillion, 588 trillion, 800 billion, approximately, because it only holds so many decimal places. If I'm not mistaken, the universe hasn't even been around that many seconds, so it would take us too long to actually list them all, much less make histograms and see if they're bell-shaped, if they're normal. So, how can we answer the question, when will these x bars be normally distributed? And when they are, what good does that do us? Well, we'll get into that in a moment. But first, let's answer the question, is the sampling distribution of X bar normal? In other words, if I could take from a population every sample of a certain size and make its distribution, so list all the X bars and the probability of them happening, under what conditions will its histogram be normal? And keep in mind that if we have a ridiculous number of samples, then we can make skinnier bars because these wouldn't take up much space, and it would start looking more and more like a probability density curve, a bell curve, if you will. Except it may not be bell curve because it may not be centered. It might be a skew to the right or skew to the left or something like that. But the answer to this question is actually known and easy. The answer to this question is something called the central limit theorem. And it goes something like this. The sampling distribution of X bar, that two-column table that lists every X bar's value and the probability of it happening for a given sample size, n. Let's put some commas around the phrase for a given sample size n. Will be approximately normal, and that's all we need, close enough to being normal. Under one of two conditions. Now, both conditions can be met, but you only need one of them. Number one, the original population is approximately normal. In other words, when I do the first histogram, it wasn't approximately normal. But for a large enough population, it might look approximately normal in its histogram. So if the original population is approximately normal, bell curve, then when we do this sampling distribution thing, it will also be approximately bell curve. But that's not the only condition that guarantees your X bars will be distributed normally. Because frankly, sometimes we just don't know if a population is approximately normal. However, there is something we have control over. The sample size is at least 30. Actually, before I write that down, let me check this author's perspective on it. Some authors say at least 30, some authors say greater than 30. This author says greater than 30. And I have asked people who know more statistics than I do, what's so magical about the number 30? And almost every one of them, in fact all of them said, well, it's just the number that works. As a theoretical mathematician, that drives me crazy. There has to be enough reason they selected 30. And this is something we have control over if our population is large enough. So if we have a population of a size so large, we don't know what it is. But we say, we'll pick samples of a certain size and it's bigger than 30, and their X bars will be approximately normally distributed. So in your homework, when it asks you, is it appropriate to use the central limit theorem? What they're asking you is, are either of these true? So if either of these are true, they'll tell you the first one and you can easily observe the second. Then yes, the central limit theorem applies and the sampling distribution is approximately normal. Now it goes deeper than that. I meant to do this on the previous table, which I can still see the remnants of, where we had the 1.3 repeating, 1.6 repeating, et cetera, et cetera. I wanted to find out what the mean of that distribution is. That's okay. Time for that is come and gone. So I'll just tell you what the central limit theorem says. If the sampling distribution is approximately normal, if the sampling distribution is approximately normal, know it's approximately normal, there's a formula for calculating its mean and standard deviation. And again, I wish I hadn't erased this, but back here we had 1, 1, 2, 3, 4. This has a certain mean, this has a certain standard deviation. The mean would be pretty easy to calculate. It's just the sum divided by 5. The sum is 11. 11 divided by 5 is 2.2. What's the standard deviation? Honestly, I don't know off the top of my head, but if you give me a second, I'll calculate it real quick, because I know the mean and I know the formula. So 1.2 squared plus 1.2 squared plus 0.2 squared plus 0.8 squared plus 1.8 squared equals divided by 5, and we'll square root that. So the standard deviation for this guy is approximately, well, we'll just say equals 1.1662. I just cranked it out real quick. But a natural question, at least from a theoretical perspective, is if we know the mean and standard deviation for the original population, and we have this distribution of all the x bars, can we figure out this distribution's mean and standard deviation, and is it related to that one? And the answer to both questions is yes. If the sampling distribution is approximately normal, then I need to introduce two new variables to you. One is a mu with the subscript of x bar. Mu is the mean of a population, x bar is x bar. What this means is the mean of all the x bars. In other words, and I really wish I hadn't erased this, but I think it went 1.3 repeating, 1.6 repeating, and then there was a 3, and then there were some couple of 2s. Was there only 1, 2? Well, let me reconstruct this. 1.3, 1.6, because I think I remember what the histogram looked like. 2.3 repeating, 2.6 repeating, 3. I remember this one was 1, and this one was 1. And I want to say it was 1, maybe I can see the ghost image of it. I'm kicking myself for not writing this down. Wait, there's the ghost image. I erased it really well. One of these occurred 3 times, and I know you're probably screaming, was that one? Was that one? I think it was this one. This was 1, so that's 5, 6, 7, 8, 9, 10. I think it was 113221. Well, we'll say it was. So if I have this number once, this number once, this number 3 times, this number 2 times, this number 2 times, and this number once, what is the mean of those, and what is the standard deviation of those? The mean of all the x bars is called mu sub x bar. So it's literally what it says, the mean of all the x bars. And it turns out that the average of all the x bars is equal to the average of the original population. Easiest formula in the world. The average of all the x bars equals the average of the population. And there's a relationship between the standard deviations. The standard deviation for all the x bars is called sigma sub x bar, which makes sense because sigma means standard deviation of the population, in this case the population of all 10 x bar values. But the formula for the standard deviation of all the x bars is not just sigma, but rather sigma divided by the square root of n. And why is that important? Well, think about what happens to this when the sample size gets larger. As the sample size gets larger, this fraction gets smaller. Well, what does that mean in terms of the bell curve? The standard deviation is how spread out the data set is. So if you have a bell curve and you pick larger and larger sample sizes and this gets smaller, that means your bell curve starts doing this, getting real tall and skinny. That's going to be really useful when we get to confidence intervals, which I plan to get to later this week. Alright, so what does all this even mean? Well, what it means is if you take all the samples of a certain size and all of their sample means, then I know what the average of all the sample means is, and I know what the standard deviation of all the sample means is. That's all this is. Average of all the sample means, standard deviation of all the sample means for a given sample size. So let's go back to the previous problem just for a second, where we had 1, 1, 2, 3, 4, And I just like drawing the second one red, I don't know why. And although we didn't calculate the mean and the standard deviation earlier, I'm telling you right now that the mean and the standard deviation are 2.2 and 1.1662. If n equals 3, calculate mu sub x bar and sigma sub x bar. You actually have a homework problem that gives you this information and asks you to calculate this. It's actually really easy. Easiest formula ever. The mean of all the x bars is equal to the mean of the population, which was 2.2. But the standard deviation of all the x bars is the standard deviation of the population divided by the square root of the sample size. So the standard deviation of the population is 1.1662. The sample size was 3. And if we divide that out, we get something. 1.1662 divided by the square root of 3, about 0.6733. And these are numbers that we're going to be using in some examples here in just a moment. But the important thing about this video is all of your x bars, all of your sample means in a given situation will be approximately normal, approximately bell curve, if you know one of two things. The original population from which you sampled was normal, which you may or may not know, or the sample size is greater than 30, which you will know because you'll know the sample size. If either of those happen, then the mean of all the x bars is just the mean of the original population, but the standard deviation of all the x bars is the standard deviation of the population divided by the square root of the sample size. In the next video, I'll show you how this information can be used to calculate some probabilities. Whew, that was a long video. Sorry.